the next topic we have is mass energy equivalence. And this is a really big deal. You've seen this equation before, I'm sure, in some form, but you probably didn't really understand what it means. But if you take a close look at it, it has some rather alarming ideas. This is basically an equation in which you have, it's a linear equation between energy, which is measured in joules and mass, which is measured in kilograms. And this factor, this constant that equates them together is the slope of the line that you create when you're graphing these two together. This is what we call the speed of light, or the speed of electromagnetic radiation, because light is a form of electromagnetic radiation, squared. That's your constant. Now, the speed of electromagnetic radiation is 3 times 10 to the 8th meters per second. So when you square that, that becomes 9 times 10 to the 16th meters squared per second squared. And when you take kilograms times meters squared per second squared, you get kilograms meters squared per second squared, which is a really clumsy label to put on something. So they've given that abbreviation as being joules, and that's where that comes from. Okay? So, what we're going to look at is how we can calculate the amount of energy that is coming off when you change a mass to energy. Now, when would that happen? Well, when you create a bond, you are taking some of the mass and you are changing that to energy, holding them together. This is called bonding energy. Bonding energy is considered a form of molecular potential energy. That potential energy is from that very process. So we can calculate the amount of energy being used then, because when you break bonds, that energy then is released. And the amount of material you had after that reaction is completed is less than what you started with because of the conversion of that mass over to some form of bonding energy. There's an example I gave you in the script. It says to calculate the energy of 1 mole in the equation C solid plus O2 gas yields CO2 gas. The 1 mole of carbon is involved in this. And the delta H for this, and this is the key to this, is negative 393.5 kilojoules per mole. Now, we've already talked about how we use joules in the E equals mc squared equation. So what we're going to do is we're going to convert that right away to joules by converting 1,000 joules per 1 kilojoule. And this will give us then negative 3.935 times 10 to the 5th joules. We plug that into our equation, E equals mc squared. The E then is the negative 3.935 times 10 to the 5th joules equals the mass. And that's what we're trying to solve for, how much mass was lost to create the bond and the amount of energy being given off when it's broken, times 9 times 10 to the 16th meters squared per second squared, or 3 times 10 to the 8th meters per second quantity squared. So we divide both sides by that 9 times 10 to the 16th meters squared per second squared. Cancel out, and as we showed, meter squared per second squared cancel out the meter squared per second squared here, and that's going to leave us a kilogram value. And so you crunch the numbers on your calculator, and we get 4.37 times 10 to the negative 12th kilograms, or if you want to think of it in terms of grams, we can convert that. You don't have to do this, but I'm just doing this for a comparison's sake. 1,000 grams per 1 kilogram will give us 4.37 times 10 to the negative 9th grams. Now, to give you a little perspective, this quantity right here, the negative 393.5 kilojoules per mole, is a tremendous amount of heat. Under normal chemical reaction conditions, that's sometimes enough of a quantity that's going to allow you to power your house, because you're dealing with 1 mole of carbon. Carbon is only 12 grams. And if you were to somehow create this reaction that gives off this much heat, of course you're never going to heat up your house with this, but combustion reactions, this is kind of a combustion reaction, gives off a tremendous amount of heat for a small amount of mass. Well, how much mass did we change? Just about 4 nanograms of carbon release that much heat. Now that's just a tremendous amount of heat. So this is why we use nuclear power plants instead of coal burning plants to produce electricity or energy, because of small quantities creates an efficiently large amount of heat, and there's no byproducts that is released into the atmosphere unless the storage of the waste products is not done correctly. Then that's an issue. That's why nuclear power plants are so expensive to build, because the toxicity of the, shall we say, remnants of the reaction are pretty severe. But if we can find a way to make sure, and we've got processes built in, but it's just a matter of actually following through with them, that we can keep this safe and out of the hands of people who want to do damage to our society, then we're going to be okay. So let's take another aspect of how we can look at this. Another example I gave you in the script. So we want to know the mass effect and binding energy of a lithium-6 isotope atom. Okay, now lithium is element number 3, so it might be a good idea to put that down there. And so what we need to do is we need to figure out the number of protons, which of course is 3, and the number of neutrons. This is the atomic mass, and the mass of an atom is over 99.5% what's in the nucleus. So we kind of ignore the electron part of this. And so it's protons and neutrons. So if this is protons and neutrons, and then we subtract the protons, then that's going to give us neutrons. So we subtract these two, 6 minus 3 protons gives us 3 neutrons. Okay? So, in the chart that I've given you in this particular lesson,